so much for the invitation to be here. It's too bad I can only stay for a little bit, so do catch me at lunch. That would be great. So I will tell you about quantum geometry. Is this large enough? I see that it's from far. I need to write it bigger. Okay, quantum geometry. See if I can do it. Geometry and linear response. So my goal is basically to give you some intuition of what quantum geometry is based on response theory. And I believe most of you are familiar with quantum geometry already, at least Berry curvature is very, very common. So it's a slightly unorthodox way of introducing geometry, but I hope there is a physical insight that is to be gained. And this is based on these two papers. 3.5, which is the first paper with my student Ilya Komisarov, and second paper with Nish Verma, 0.5. Where we talk about generally instantaneous response and its relation to quantum geometry. So I'm very happy that I just come after Masaki, so you heard a little bit of like how instantaneous response comes to be. Okay, so basically the words that I will use will mostly be related to free fermions and electrons. This is just because the language is the language that I'm comfortable with, but all the formalism is completely generalizable, and it's in fact not assuming that we're talking about free fermions. And what I want to do is really relate these concepts with physical properties of materials that we know and recognize, okay? So let me just start by writing a very simple Hamiltonian for free fermions. And we are living in a crystal world, which means that there will be some periodic potential that arises because of interactions with ions, interactions between electrons. It will respect some periodicity, okay? And the main effect of this is that if we start with free fermions, with the dispersion, okay, we know exactly what's the mass here. This is the mass, the bare electron mass. And when we put a potential, then momentum is no longer a good quantum number, right? So it will only preserve momentum up to reciprocal lattice vectors. And we break down, so this is P, this E. We break down this dispersion into bands, okay, labeled. Let me put here some labeled by crystal momentum K. It's this. Now, if we take really free fermions and we put a potential, there will be some kind of separation of scales that happens. You will have some bands or some levels which are very, very core, which are basically dispersionless. They're electrons which are very much bound into their core ions. This is core electrons. There will also be a continuum of electrons that are such high energy that they really don't care about this potential at all. But all our fun, it's somewhere here at these intermediate energies, where for electrons, our Fermi level should be around, right? So as I tune the number of electrons that I have populating this band structure, then I can get, in the gap, I will have an insulator. I can get metal if this crosses, if there is a Fermi surface, right? There will be here a Fermi surface. I can tune my chemical potential or Fermi level into a crossing to have a Dirac point, Dirac physics, and so on and so forth. So really, what we are usually talking about is some low energy theory associated with these bands. Now, what I want to ask myself is, so if I'm here, if these are the electrons that I have that we really get to play around with, what are their properties? For example, what is their mass? How do I talk about their mass? Okay, so one thing that we can do in order to talk about mass, we talk about an effective mass, right? So we had p squared over 2m. So here, the bare electron mass can be given by this curvature of the band. If I now put this potential and I open gaps, my band's dispersion is going to change slightly or a lot. And I, for example, can associate an effective mass to this band based on the curvature of this band around the Fermi level. So this will go something like k squared over 2m, let's say here, Fermi surface. Okay? So that's an effective mass. And then I know if I do semi-classics, if I look at transport theory and so on, I am interested, mostly this effective mass is what's going to play an important role. So let me just, before that, say something else about these states. These states now are eigenstates of my Hamiltonian, which are characterized by a band index that tells which band we are in, and my crystal momentum. Okay. And these states, which are labeled by crystal momentum, I call them Bloch states. Okay, they're completely extended in real space, and they're going to be eigenstates of translation, lattice translations. So T, lattice translation by Bravais lattice vector R, then K dot R psi alpha K. How do they look like? This phase factor here, this Bloch phase, will correspond to some overall envelope, the function of R. There will be an overall envelope. So this is the unit cells. There will be an overall envelope given by e to the I k r. And then my wave functions, my Bloch states, will look somewhat like that. Okay. So we can the usual thing to do is to separate this Bloch states into this phase factor, which is associated with their momentum quantum number, and a cell periodic part, such that you remove this phase factor and you just have repetition. So this is psi. You just have repetition of kind of atomic orbitals, okay, which are all the same, independent of the unit cell. Okay, so here's a very basic tools that we have to describe bands in solids. And I want to go back to this idea that if I want to talk about the physical properties of the system or how the system responds, I need to know these quantities, such as the effective mass associated with the band. And how do I properly define this? That's one mass that I can define. I can define another mass, which is basically, instead of asking what is the band dispersion, one thing I can do is that I can apply an electric field, very fast electric field. I shake the electrons extremely fast to the point that they don't know where they will hop. They will forget they are in a lattice, and you will somehow know how to pick up again the bare electron mass. So there's some information about the bare electron mass, and that information is in when you apply an electric field extremely fast, right? So we'll call that instantaneous response because it's extremely fast. Then you start being sensitive to the bare electron mass again. So how do you do that? You can do that by finding the resonance of your electrons, by finding the resonance frequency or the plasma frequency squared, which is NE squared tau, NE squared over the bare mass of the electron. Okay, so then, so this mass is certainly going to be different from this the mass of the dispersion that you get. So the resonance frequency is basically the best frequency where you can absorb energy in the most efficient way possible. Okay, so where basically all your energy is in conducting energy. Another way of finding this plasma frequency or recovering this bare electron mass is what also we heard in the previous lecture, which is the F-sum rule. So if we integrate over all possible frequencies of my lattice, of my oscillator, I have the F-sum rule, which tells me that if I integrate from 0 to infinity all frequencies of the conductivity, so mhe, I pick up again the bare electron mass, and this is equal to pi over 2 epsilon 0 frequency squared. Okay, so the entire spectral weight that I have in my system has been distributed by different energies, and in the end of the day, I know that if I'm looking at instantaneous response, I pick up the effective mass, bare electron mass of the electron. So if I'm at very long, slow response, I am going to pick up the mass of the Fermi surface. And if I'm talking about a very quick response, I'm going to pick up the bare mass of the electron. Now, one thing that I can do, and that it's also kind of natural to do if I'm looking at a specific low energy, and if I want to make a low energy theory of my bands around the Fermi level, is not integrate over all possible frequencies. So when I do this integral, in order to get bare electron mass here, and this is the density of electrons, so it's actually the total density of electrons. So I need to integrate from all of these transitions, all of these optical transitions, from core electrons to continuum, everything I have to integrate in order to pick up on the bare electron mass. So talking about the bare electron mass most of the time doesn't mean anything to us. It's not really that important. Okay? Maybe a more interesting thing to do is to focus ourselves of frequencies around this low energy regime, which means that I'm going to put some cutoff in the frequencies that I am integrating the optical conductivity. And when I do that, then of course I have a renormalized density, I have less electrons, and I will also have a renormalized mass. And now this renormalized mass, I'm going to call it mg. So we found two ways of talking about the mass of the electron. One about how it responds instantaneously, another one on how it responds very slowly. We have m star, the Fermi surface, and there's absolutely no reason for these two to be the same, right? They will be generically quite different. Okay, so the question is, how do we talk about these quantities like the optical mass of an insulator, the effective mass of a metal, and other properties like the dielectric constant and so on that will appear in a completely generic way. And I think I'm not yet completely. Okay, maybe it's better to just clean this up. Do interrupt me with questions if there are any. Yeah. Absolutely, it will. So, yeah. So when you say M star, so these are, okay, if you can fine tune a situation where they are the same, but in generically they are completely different, okay? And the bottom line of this talk, it's really going to be that this guy knows about dispersion. This guy knows about wave functions. And a very compact and neat way to talk about wave functions is to use quantum geometry. Okay, so let me now justify this, okay? And to justify this, let me tell you about a puzzle that in band theory was around for a very long time, which is really how do we talk about a dipole moment or polarization in solids. It's a problem, and the problem is coming from the fact that in solids, if you're just thinking about polarization, okay, polarization in solids, if you're just thinking about the dipole moment of an electron in a molecule, for example, we know how to calculate it. Polarization is just going to be the expectation value of the position operator. So this is the charge density, which is just sum over k, r squared. And it's not a problem because you know exactly where your nuclei is. You have an electron, and you will find where the electron cloud is somewhat displaced from your nuclei. However, if we have a solid, the situation becomes quite more complicated. And this is pretty much a picture taken from David Vanderbilt's book, which I really recommend everybody to read this wonderful book, where basically imagine that we have the electron cloud somewhere in a periodic lattice. Now, we see a few problems with this when we try to define polarization here. The first problem is that if we define polarization as the integral of r rho r, this is an unbounded operator. In an infinite crystal, this thing goes to infinity, so this completely blows up. So that's an issue. There's another issue, which is what is your point of reference? So if you integrate the charge density in this unit cell, let's say, you see that the electron cloud is symmetrically displaced around the positive charge, which means that the polarization, you would get an answer, the polarization is 0. But if you take this unit cell, then you would get a dipole moment, right? So the answer that you're going to get is going to depend on the unit cell that you choose. So this is a fundamental problem. It's not just a problem on how I set up the the problem here, it's really that it's fundamentally impossible to determine P just by the charge density. And this is noticing this, that it's fundamentally impossible to find this answer just with the charge density, is what we refer to as the modern theory of polarization. So like the recognition that this is not possible to do. So what is the trick to solve this problem and be able to define polarization in a periodic system, in an infinite and periodic system? The trick is the following. Position operator, let's talk about this as the derivative with respect to momentum, but now momentum is not a good quantum number. So this is the derivative with respect to crystal momentum. It's not going to be exactly the same equation, but it's going to solve the issue for us. And instead of the density, we should talk about the projector into the ground state, which in this case are the Bloch states of the bands which are filled. So what you get, so this is, let's take the projector. I'm using P when there's too many P's. This polarization will disappear soon enough. Okay, so this is the projector, sum over K into the Bloch states, U alpha K. Let's say projector into the band alpha, U alpha K. And now what we get is the correct expression for polarization. In solids, which is E sum over alpha field bands, integral over the Brillouin zone, dk uk alpha, idk uk alpha, which I can write this in a more compact way as trace of P, the projector, into the field states, times the position operator, which is nothing but the expectation value of the position operator. So in principle, this is a three-dimensional vector. So let me just keep some indices here around. Okay, so this is the correct way. So now you can recognize that what this is the Berry connection. So what this is picking up is on how the wave functions in momentum space, the Bloch wave functions, the cell periodic Bloch wave functions, change as momentum is changing across the Brillouin zone. And we can do a very simple example that, okay, I'll try to move faster than that. A very simple example, which you probably all have seen before. So I will be relatively fast, which is the SSH chain, where we have a unit cell with two sublattices A and B with inversion symmetry. And this here is telling you the hopping T. This is the unit cell. Now this is just a tight binding Hamiltonian for this, which it's off diagonal, tk star 0, with tk equal to t minus delta t plus t plus delta t e to the I k a. So this corresponds to the hopping inside. I put minus and plus. Let me keep the note, keep the convention right. So the hopping inside of the unit cell and the hopping outside of the unit cell. And now my Bloch states, the band structure of this thing, it's going, there will be two bands because I have two sites in the unit cell. And the wave functions for the bottom band, they will have a contribution in the I sublattice and in the B sublattice. And generically, this is going to be given by E theta K. 1, where this theta is the argument of this function. So I can see that there's going to be 2 phases associated with whether delta t is larger or smaller than 0. For delta t larger than 0, I will get that the expectation value of r, here just is 1d, which is going to be given by a over 2 pi into 1/2 integral of theta k of this function here. That is going to be in the phase which is what we call topological phase, or I don't know if you want to call this topological phase. There's one phase and the wave functions go around like this, and you'll get that to be 2 pi, which means the expectation value of the position is going to be a over 2. What does that mean? It means that the center of the electrons, the center of charge of the electrons, is in the center of the unit cell. And I will get another phase where this integral, line integral of the Berry connection, it's going to be 0, which means, actually I said the wrong way, right? So this guy is 0, this guy as r equals 0, and this guy, which is on the edge of the unit cell, as r a over 2. So these two situations are distinguishable, right? And the way that we can distinguish between the two is really because of the phase of the wave function either winds or it doesn't wind.
So for the definition of polarization, see how sometimes you include ion charge, sometimes not.
That's because, yeah, we should include in terms of polarization is the charge times the position of the electron. But I'm going to forget about it sometimes, just because of not being very consistent. Yeah.
Wave function is only the electron wave function.
It's the electron wave function.
Where does the ion?
The ion, so the ion is not part of this. This is just on the background. So this is in order to talk about the center of charge of the electrons themselves, and you basically set up your problem such that you have a lattice, and that's just the background potential VR that you have. Okay, you don't keep track. Yeah.
At the beginning, you said there was an intrinsic ambiguity determining the polarization.
Yes. Yes.
What's the ambiguity there?
No, so this fixes the ambiguity. Defining the polarization this way fixes the ambiguity. Okay, there's 2 ambiguities. Actually, I should be a little bit more careful. There's 2 ambiguities. One is related to where you put the ionic charges, and that's a physical ambiguity. It matters where the electrons, where the physical positive charges are. And then there's a non-physical ambiguity, which is fixed by defining the polarization this way, that you need to keep track of the phases of the wave function. So in order to define exactly the center of charge of the electrons, irrespective of the position of the ions, that we need to keep track of the phases of the wave functions. Okay, so that's correct, up to an integer. Okay, so now this type of so the 2 phases of the SSH chain the two phases of the ACSH chain that so let me just say that too. If we don't fix the ambiguity of the ions, there's really just the difference between the two phases is what you can keep track of. What you cannot keep track of, which is topological, let's say. Yeah.
Gate charts for like the UK can have a K dependent phase.
So, yes. So this gets rid of that. So if there's an overall phase factor, this gets rid of that. It still gets rid of that. So the idea is that so you can rotate everybody. The winding will not depend on that. So that's important. Okay, so let me. There's of course a kind of a large gauge transformation that you can do, which really would shift the unit cell, just shifting the center of the unit cell, and that would shift. Okay, but so there's a lot of ambiguities. You want to somehow keep track of some ambiguities, which are physical. So the fact that you have, so basically in the SSH chain, you can have, maybe the way to do it is this way. You can have either the charges on the center on the ions, or centered on the bonds. This is actually a pretty common thing. So the way that you so the center in the center of the unit cell or in between unit cells, this is a pretty common thing. So if we're talking about semiconductors, all semiconductors, silicon, gallium arsenide, and so on, then you have 2 sites per unit cell. This is kind of in the diamond lattice. And your electrons are actually living on the bonds. This is because they form what's called sp3 bonding. And so you have the energy spectrum of that is that you have the filled bands are bonding bands and the unfilled bands are anti-bonding bands. So it's a pretty common thing that you have this what's called a quantized Berry phase in semiconductors. So now, in order to, basically what I just told you, and the main message that you should take from here is that if we want to talk about the dipole moment, if you want to talk about polarization, we need to care about wave function phases. And how they wind Berry phases. Which means that if we want to talk about transport like conductivity, which conductivity is nothing but how the current is changing as I put an applied field, and the current is nothing but the change in time of the polarization. And so this is pretty much delta J plus delta E, which is to P delta T, or maybe quantify PDT. So the rate of change of polarization, if I want to talk about conductivity, I better keep track of all of these phases informations of the Bloch states in a solid. So with that, let me go to the Kubo formula to linear response. So what's the physical setup here? We have our Hamiltonian. We're going to put some time-dependent perturbation, which is going to be vector potential. And that will generate a current in our system. I am just going to be talking about an electric field. Electric field is basically dTA. Now, this electric field is going to be time dependent with a frequency omega. And basically, linear response will tell us that you'll generate a current at the same frequency. And so mu omega omega mu omega. Now, conductivity, the rate at which we create that current. Now, the Kubo formula, you do linear response, and you'll get that conductivity, mu omega, is equal 1 over I omega JV mu. You have a diamagnetic contribution to that because when you introduce a gauge field, you're basically shifting your momentum, just like we saw in the previous lecture. So we're going to have a p squared over 2m will lead to a contribution, a perturbation that is proportional to a squared, and one is proportional to a. So we'll have a diamagnetic contribution, which is the higher order a squared contribution. And then we will have, a current dt, and this part here is your current correlated susceptibility. Sorry? The indices, sorry, so this is for the diamagnetic, this is for paramagnetic, and mu and nu are just the spatial directions. So this mu and nu are spatial directions always. The current, yes. So I'll keep the indices in the conductivity. So I'll keep track of whether the current is generated in the direction that I apply the field or transverse to it. Yes, that's correct. Yeah. So yeah, I need to, that's right. So this J will have a part which is JP and a part that it has a JD times, yeah. So this has the diamagnetic contribution at all. So as well. So actually, I should be careful and put here an A as well. But I don't want to mess it up. But I think I will also put an A there because this is the diamagnetic part is a second order an A. So this is actually not very. This diamagnetic part is not very important to us. It will just all cancel out. What we are interested is in the interband contributions. And when we write down current correlator dt omega t some mn integral over the Brillouin zone f and k mk j mu n k j mu m n k e to the I omega m n t. And now this current is really the only one, the paramagnetic one is the one that we care about. J mu is equal to E I h bar Hamiltonian R mu. So the matrix elements of the current operator are going to be Mn, right, omega Mn R mu Mn. Here, omega Mn is En minus Em over H bar. So we're just wrote down the current operator in the matrix elements of the in the band basis. Now, what this is going to turn out to be it's going to be divided into nicely into two parts. So let me just say one thing. I am kind of hiding the momentum indices. I'm just doing an integration over the entire Brillouin zone. So I'm going to hide a little bit the momentum indices over here. So when I talk about FNM, you should read FNK minus FMK. And it's going to just become the following. This piece d mu nu, we just write it. It's j d mu nu minus chi j j omega equals 0. Okay, so what you get from the full Kubo formula, when you just represent it in the lemon representation, you get a part here, which is a peak at omega equals 0, which is called the Drude weight. That comes from contributions from the Fermi surface. So if you have electrons and they are free, they're going to be contributing to the Drude weight. And you will have a part of the conductivity, which is due to interband transitions. And now you can see one thing, which is these contributions from interband transitions, they're going to be due to dipole-dipole, the fact that you have interband contributions of the dipole operator. So your dipole operator allows you to go over the gap. Yeah. Okay, so RMN, mu MN is just U M K I E K mu U N. Okay, so this is the matrix elements, the matrix elements of the Berry connection. That is all in the Drude weight. Sorry?
Just in formula above, you have like.
What about it?
Just above, like the current mu is equal to minus I.
Yes. That's right. So if, yeah, I shouldn't have said anything about metals. Let me basically, I wanted to keep here to Drude weight just for us to remember if there's metals, there's contribution to the Drude weight. If you have a metal, your current operator will have other terms associated with not keeping it's not diagonal in momentum. So this contribution here is going to, there will be some slight, I don't have time to really put all of the contributions here. So what I'm going to do is, if we just have insulators, let's forget completely about our contribution from Drude weight. And the only terms that we have contributing to the position operator are our Berry connection terms. Okay? And you can ask me later. I'll show you the full for metals the subtleties in defining the current operator. Okay, so let me take the DC limit. Let me take insulators, first of all. Let me not make my life very hard. Let me call insulators. And let me take the DC limit. So sigma mu nu at 0 frequency, it will only have the interband contributions and h bar sum mn fmn omega mn. At omega equals 0, the denominator also goes to omega mn. So these guys cancel out. And you just have, oh my God, okay. You just have the contribution from the position operator. Now this guy here has both a symmetric and an anti-symmetric part. So I can write R m n mu R n m nu equals G m n mu nu plus I over 2 omega m n mu nu. These are just names. This is the symmetric part. We call it quantum metric. This is the anti-symmetric part, which is called Berry curvature. And you see that the distribution function here, the Fermi factors, are anti-symmetric, which means that this guy will drop out, and we're going to only pick up the contribution from the anti-symmetric part, which is the Berry curvature. So when we put it out there, we see that this is Fn minus Fm. This turns out to sum over. We can separate the two terms. We swap the order of one, and we just get Mn Fm, R Mn mu, R N M nu minus R mu Mn, or Mn mu, which is nothing but minus I omega Mn mu nu. And you may recognize this as this is the antisymmetric part. The only antisymmetric part that we're going to have of position, it's going to choose x and y, right? So it's going to be the only term that we're going to have. So this is going to be e squared over h bar sum m f m x m n y n m minus y n m m n x m n, which is nothing but e squared over h bar, the integral over the Brillouin zone. Let me put it here explicitly, commutator of x and y. Okay. So the commutator of x and y in momentum space, if you're looking inside of the Brillouin zone, x is going to correspond to a little step in momentum along x, and y is going to correspond to a little step in momentum along y, right? So what this commutator is basically taking a little loop in the Brillouin zone, and it can pick up a phase. That phase that this is picking up is the Berry flux, and once you integrate it over the entire Brillouin zone, there's an I here, you get 2 pi IC if you have a Chern number. So this becomes e squared over h. The 2 pi I cancel out, MC, and that's the TKNN formula. So you see that the interband contributions to the conductivity coming from this position operator, it's going to lead you to get your expression for the TKNN, so for the Chern number. So the whole conductivity, and of course, yeah, so this is only the antisymmetric part survives, so that's the whole conductivity. Now, I want to look a little bit more at that position commutator that we get there, which basically xy, I can write it in the same spirit as before, as the projector into the field states times x times y minus projector times y times x. Now let me put here inside a 1, and that 1 is going to be given by the projector into the field states plus the projector into the empty space, the states, the complementary projector. And we see we can rewrite this thing as trace p x py minus trace py px plus trace px qy minus trace py qx. Now this trace is cyclic, so you see that these guys don't contribute, right? They cancel out each other. So what's happening here is that this commutator, which is the Berry curvature contribution, it's going to be the antisymmetric part of a more general operator, which can be defined in the following way: P R mu, Q R nu. And we call this guy the quantum geometric tensor. You can see something nice. While when we were talking about the polarization, this is basically the center of charge of the electron cloud, is the first moment of the position operator. What is appearing here, what's appearing in the conductivity, is the second moment of the position operator, is a variance. So P is a projector into field states. Maybe I'll write here. P is a projector into the field states. Q is a projector into empty states. And what this guy is telling us is P R mu Q, Q R mu P, is telling you that there is basically a variance, R mu R nu, R mu R nu, of the position of electrons due to this kind of like virtual transitions, quantum fluctuations, which are actually renormalizing the position of your electrons. So how do I interpret this quantity, the quantum geometric tensor? It's the variance of the position operator, second moment, is if I have an electron, I'm in a situation where I have bound electrons, I'm an insulator. Okay, let's forget metals, I just have an insulator. All my charges are bound, but my charge is in one particular spot. And now it can kind of like tunnel through a virtual transition and appear somewhere else, right? And there will be a size, same way that there's sizes to orbitals, it's the same effect, right? The sizes of orbitals of where you don't know where your electron is. And that size is going to be described properly in a periodic system by the quantum geometric tensor. Now, if you have a normal insulator, like I was telling you that all the semiconductors have the electrons living on the bonds, that quantity is going to be relatively large because the electrons kind of like will hop between the different bonds that each each silicon is going to be connected to. Right? So this is going to be relatively small, relatively large. Now, if you have a situation where you have a Chern number, where you have a topological invariant, it can be that there's not only a symmetric part, there's also an antisymmetric part, x and y, which tells you that there's kind of a vorticity to this. Every time you jump up and down, you might prefer to go a certain direction. Okay, so that's maybe the quantum mechanical way of thinking about the cyclotron orbits in the quantum Hall effect. Now, this is called quantum geometric tensor for a reason. And you will hear a very different way of talking about quantum geometry, I suppose, in Eslam's talk later in the week. But why we think about that, in that sense, this comes from if we focus on a specific band in momentum space, and you have your Bloch states. Let's take alpha equal, let's take the index alpha out. Let's just think about one single band. Then in momentum space, if you resolve this operator in momentum space, you get the following. UK, 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 E, U, UK, which in UK plus I over 2 omega mu in UK. The antisymmetric part is the Berry curvature, as you know and love, and the real part and symmetric part is the quantum metric. Now, this is a quantum metric. Why? Because once you are thinking about your band and you take a state and you just parallel transport it a little bit somewhere else, a UK plus delta, then you see that as you do this adiabatically, you're actually going to lose some norm in this state. And the norm that you lose, UK plus delta K, it's going to be given by the real part of this metric. So now that is a rather abstract idea, but in terms of if you want to visualize what this guy actually means, it means this. It means that there's in the ground state, there's an uncertainty in position. There's a size. There's a size to orbitals. It can be coming from their original basis states. That's usually not what we care about that much, but there's also some size of the orbitals that can appear because you have an Hamiltonian and there's quantum interference, and it just changes how do the bound states look like in the ground state. And so this is the quantum metric. I will generically talk about G as just using just G as the integral over the Brillouin zone of G mu in UK. And I'll also take the trace in the indices, so that will correspond basically in 2 dimensions to x squared plus y squared. The same, if I were to take the integral over the Berry curvature, I will get the Chern number or I'll get nothing. Now, while if I take the integral of the Berry curvature, I'll get an integer, and that's guaranteed because it's by a topological invariant, it can only be an integer. This guy is a positive semi-definite function in the Brillouin zone, which means that it's really a quantitative thing. So it just tells you how big the sizes of these orbitals are, of these bound electrons are. It can be any number. So if you think about 0 is being like point charge completely pinned down, right? That will be something completely trivial, let's say, to very large, very large. It can also be very large. So let me just show you, for example, what happens if I have a transition, topological phase transition, like the transition in the SSH chain, where I switch the spot where the center of charge is localized from the center to the edge of the unit cell. Let's set it 0, larger than 0. If I look at the total metric, so this guy is in the center of the unit cell. If I am basically in the dimerized limit, the metric here will be 0. The electrons will be all collapsed to the 1 point. If I am on the other extreme, in the other dimerization, the electrons are kind of bouncing off between the two edges of the unit cell. So there's a minimum size to my electron cloud. And what do I see as I go to a topological phase transition is that it diverges. So basically what this is telling you is that electrons, as you get closer to the phase transition, are getting more and more delocalized, and then they rearrange themselves. They get completely delocalized over the entire lattice, and then they recombine. And now they have a certain minimum size that they can take. So this will be in the SSH. Same exact picture will be if you were to consider, for example, the Haldane model, where there's a Chern number. And here, so here will be just x squared. If you look at something that has c equals 0 to c equals 1, you would have the same divergence. This now will be x squared plus y squared. And there will be a minimum value that this metric could take, which is 2 pi c. So basically, we get this condition that the trace of the metric, it's always larger than 2 pi c. That's called the trace condition. Okay, so there is some cases, very, very special cases, where it will saturate this inequality. So how do we read this? Basically, if we want electrons to have a cyclotron motion, it better have some size, right? They need to have some size. So that's always the case, that there's any type of obstruction, any kind of topological obstruction. In this case, is an actual topological obstruction. This case is what we call the obstructed atomic limit. Just means that the center of the unit cell is not there. It's not coinciding. But that's the case for the SSH chain. It's also the case for all covalent semiconductors. Then there will be some minimum size necessary for the electron orbits. Okay, I am so out of time. So let's. Yeah, but I have a lot to say. Okay, so let's see. Let's see if I have. Okay, so then let me rewrite now, go back to conductivity, okay? And let me write my quantum geometric tensor in the same basis, the lemon representation, as I wrote before the conductivity. And M. So why do you see this? Basically, this tells you N's are filled, M's are empty, right? We have P and Q, and position. And I'll write here also the interband contribution to the conductivity. Okay. So this is quantifying the interband contribution, dipole-dipole transitions. And this is quantifying how much of these dipole-dipole transitions are contributing to conductivity, to optical conductivity. Now, of course, I need an electric field or something to induce these transitions. I need a frequency here, right? So if I want, you know, they're similar enough. So I want to describe this guy as a function of this guy. I want to make it more obvious which contributions of conductivity come from geometry, coming from the wave functions. So one natural thing to do is to say, well, if I have an electric field behind on my background, then every time I go and do these virtual transitions, interband transitions, when I go up and come down, some time has passed, right? Because the Hamiltonian is not static anymore. So which means that I went up on some time t, and then when I went back down on some time t prime, things could have changed. So it's very natural for me to just simply define the following quantity, where I time evolve my position at two different times. And when I time evolve, I pick up phase factors associated with the energies. So I get Nm, Fn, 1 minus Fm, Rm, n mu, Rn, m nu, e to the I, omega mnt. So I just get this phase factor here. Okay, so now this quantity, which is basically trace of P, R, T, Q, R, T prime, should contain all of the information of the interband contributions to the conductivity. And it does. So first thing that we should note is that this guy is not Hermitian. It's going to have an Hermitian and anti-Hermitian part. So there will be a symmetric and an anti-symmetric part. So we care about the anti-symmetric part of this. Mu of minus t. And then we can write conductivity in the following way in the time domain, equal to I e squared over h bar dt, q antisymmetric, mu of t. Okay, so that's the entire Kubo formula. Just another way of writing it. If you do work out all of the details with the metallic part, which is very more subtle, and I shouldn't have even touched it, but we have it all worked out. It stays the same, so that actually contains everything. So basically, what this is telling you is that this this like quantum uncertainty in the position, there's also, you can also think about it as the time evolves, because of the Hamiltonian evolves your states, these positions are wiggling around, right? Your electrons are wiggling around just due to quantum fluctuations in the position. So there will be some velocities, there will be some accelerations and all of that. And the conductivity is picking up on how these dipoles are changing in time. They're picking up on the first time derivative of this guy. And so that is kind of maybe a nice way, at least for me, this is useful to think about in this way. And if we look at this Q as a function of time, it will just be a wiggly function whose frequency corresponds to all possible different frequencies of the different interband transitions that you have allowed to yourself. And basically the amplitude of these fluctuations that will be related to the metric. The value of this guy at t equals 0, that will be the Chern number. So another way of looking the conductivity, if we plot the conductivity as a function of frequency, now not in time domain, but in frequency domain, the conductivity, if you have a metal that has this through the peak, that only knows about Fermi surface. It only knows about the speed of the particles at the Fermi surface, so it only knows about the mass at the Fermi surface. And then we will have some spectral weight at higher frequencies, which are enabled by geometry. So conductivity, let me omega d mu nu plus I e squared over h bar sum mn f mn g mn mu nu plus I over 2 omega mn 1 over omega minus omega mn. So now we can ask what are the different geometric responses of materials. It all comes from these interband contributions. It all comes from the spectral weight that it's at high frequencies in any material. Well, first thing that we can look at is if we have a gap, if we have a hard gap, meaning no through the peak, and some energy cost until we are able to absorb energy, then we can look at how does conductivity look like for frequencies below the gap. So if there's frequencies below the gap, you cannot absorb any energy, so all of the response is non-dissipative. The first non-dissipative response, you know, is TKNN, is the Chern number, right? So sigma, if I expand this guy to small frequencies, sorry, there's an omega mn missing here. So that gets 1 over omega mn, which cuts down with this guy. And then you have 1 omega over omega mn plus omega squared omega mn squared, and so on and so forth. You can see that at each order, so this guy cuts, at each different order in omega, this guy is antisymmetric. This guy is symmetric. It picks up in the 0th order. DC conductivity picks up on the Berry curvature. That's the TKNN formula. So then you have E squared over HC. Then you have second order in omega. Second order in omega, this guy is antisymmetric. This guy is antisymmetric. It will pick up on the symmetric part. So the first order in omega, you get the following thing. Second order, omega squared, you get an omega mn over omega mn squared, so on and so forth. So this, you know, this is TKNN. This is how much energy, so you start shaking your electrons in an insulator, how much energy can you actually put in there? This is the electric susceptibility. It's related to it's the dielectric constant, related to the dielectric constant of your system, or the capacitance of an insulator. So they're all different words to mean basically the same thing. So this guy, the electric susceptibility, you see, or the polarizability, maybe that's the best word to use here, the polarizability of your medium, of your insulating medium. So it tells you how easy it is to polarize. Well, if you have a larger electron cloud, it's easier than if you have a smaller electron cloud. So that is going to be proportional to the metric divided by the gaps. Okay, so this is, but it's, you see that it's weighted matrix element by matrix element. It's not possible to isolate G, and actually I'm pretty convinced at this point that it's not, there's no physical quantity that will isolate only G without any energy prefactors. In higher order, you have this guy, which is a Hall. So this is longitudinal conductivity. This is Hall conductivity. This is Hall conductivity again. To second order, you have again the Berry curvature. So now in a material, in an insulating material that you have non-zero Berry curvature, if you send in light, it will rotate its polarization by an angle that depends on frequency, that is linear with frequency. That's related to the ratio between the Hall conductivity, the non-dissipative Hall conductivity, to the longitudinal conductivity. Now you can see that's going to be omega over G, right? And then one of the omegas will cancel out, and you'll see that the angle is going to be related to directly proportional to frequency. So I'm basically out of time, but I do want to say one last point, which is related to, you see that the non-dissipative response in insulators, it's all geometric. It's going to pick up on different moments of this geometry, right? Of this quantum geometric tensor. So by Kramers-Kronig, if we have something which is non-dissipative at low frequencies, we have something that it's dissipative at high frequencies. And these are basically the same. Which means that these low frequency quantities should appear also at higher frequencies if we integrate over all of the different frequencies. And that means, again, integrating over all frequencies means instantaneous response. If we start learning about the instantaneous properties of electrons, then we'll get to know about integrals of dissipation of all frequencies. So let's use this nice, I have another one here. So let's use this simplified Kubo formula for us to write what would look like some rules where I'm integrating over all possible dissipation okay? And I'm kind of like writing this generalized sum rule. So F sum rule we saw before tells us about the optical mass. That will be eta equals 1. Okay, but I'm writing these different generalized sum rules just weighted by various powers of omega. That tells you that you're more sensitive to things which are happening around the Fermi surface or away from the Fermi surface. And let me just write what sigma dissipative is. You can dissipate either because you have a dipole moment, the direction of your electric field, or you have a magnetic moment perpendicular to your field. So you'll have dissipation because you have, so sigma dissipative, you knew omega is real sigma longitudinal, omega nu plus an imaginary part of the Hall conductivity, omega epsilon mu nu lambda. Okay, so you can dissipate. This quantity will have both a longitudinal dissipation coming only from the metric part, which is always the longitudinal part, and it will have a Hall dissipation coming from the Berry curvature part. And what this comes out to be is equals 0. Okay, so that's all the sum rules, linear response. The different sum rules are picking up on the different moments of this 0-point motion that insulators have because they're quantum mechanical and because there's interband transitions. So if we are going to pick up eta, so there are some important ones to note here. If we take eta equals 0, I take just the zeroth derivative, so that's just the sizes. I pick up the sizes. I pick up in the longitudinal part, so if I integrate the longitudinal conductivity, eta equals 0, there is divided by omega. I pick up the metric. I pick up the size. That's called the Sousa Wilkins-Martin sum rule. Right? So then I'm picking up the size of this thing. If I look, so sorry, this is real, right? If I look at the imaginary part of the Hall conductivity, that's just the Chern number. Well, that's Kramer's chronic, the imaginary part of the Hall conductivity over omega. That's just the real part of the Hall conductivity at omega equals 0. So that's just TKNN. So that's just. If I extend my integral from minus infinity to plus infinity, I'm going to wrap up in a sec. From minus infinity to plus infinity, which you can do here because this is symmetric with respect to omega to minus omega. This one is not. So at small frequencies, at zero frequency, we only know about the Chern number. We don't know about the metric. Okay. And there's let me just also do the eta equals eta equals 1. So it equals 1. We don't have a denominator. Then we integrating the real part of the longitudinal conductivity. That's the F-sum rule, which we're going to pick up pi e squared over 2 and over the geometric mass. Now, these moments, every derivative takes 1 power down of omega mn, right, from the exponent. So this quantity here is nothing but, okay. So this is going to be equal to Fn 1 minus Fm omega mn to the power eta gmn mu nu plus I over 2 omega mn mu nu. So all of the longitudinals are going to be g times powers of omega. All of the Halls are going to be omega times powers of omega, big omega powers of big omega, which tells you immediately that the geometric mass, it's going to be omega mn times g mn. So that's what we get. So that's the correct way of defining the geometric mass in insulators in a coherent way. So we can also calculate the imaginary part of sigma Hall, and that is going to be the orbital magnetization. The orbital magnetization comes out quite naturally as well, omega m and omega m n. So you see that basically there's a consistency to the theory. You cannot decide what's the mass, what's the dielectric constants kind of independently. You need to decide who are your field states, who are your empty states, and then all of these different moments associated with the different uncertainties in the position and their velocities and all of these moments of the zero-point motion of the insulators, of bound electrons in periodic systems, they're going to be completely included in that object. And I have no more time, I think, so I'll just take a couple of questions.
I think we just have time for one question because I believe that the Diamond Hall is expecting us quite soon. So I think
That was okay.
Yeah, go ahead.
Which one of these sum rules require this cut up like that?
Sorry?
Which one of these sum rules like the up to the right you put a cut up to make the sum rule?
That's right. Okay. So here, when I put this cutoff, what I did was to define who are my field states and who are my empty states. So that's this guy. When I defined what's the density, what's the effective, what's the geometric mass, I basically defined who's P and who's Q, right? So then when I did that, and I defined what is the optical mass of my system, then I also defined a bunch of other things like the dielectric constant of the medium. Yeah.
Okay, so let's think Raquel again.